So we're going to hop into titanium. And you'll find that I think a huge number of the concepts that you guys learned in aluminum and steels translate over, right? And so you won't see a whole lot of surprising new sort of mechanistic things, right? So if we think about it, well, let's sort of jump into an example of what I mean. So here we have a pure titanium thermodynamically is HCP at room temperature and pressure, and goes up to BCC, transforms to BCC at higher temperatures. So if I were to say that a alloy was a strong beta or BCC stabilizer, right? What would you expect that to do to the transist? Right, push it down, right? Where in the two-phase region, where would you expect to find that alloy? Which phase is it going to segregate to? The beta phase, right? So, there's new stuff, but a lot of the same sort of the core ideas are all going to be things that you've already seen. The biggest, I think, the biggest new introduction is now you've got a HCP metal, right? So what does the fact that alpha is HCP going to imply about properties and processing? Anisotropy. Okay. Do you expect pure alpha to be ductile or brittle?
Brittle.
Yeah, more on the brittle spectrum, right? Right. We don't have nearly the available slip systems that we do. Well, the number, but the activation is not nearly as easy. Okay, so we do have a volume change, right, with at the transist, right? So BCC being the more open structure, right? Closed pack to BCC, we get a volume change. Physical properties these are just here for your reference, but note the Young's modulus of 109 gigapascals, and density is on here somewhere, right? So density of, say, 4.5 kilograms per meter cubed. So where does this combination of properties put it with respect to steel or aluminum for strength to weight?
In between.
Right. Well, significantly higher for strength to weight. Right? So it's 60% of the strength of 60% of the strength of steel, about 50% more than aluminum, right? But a density that puts us in terms of strength per weight significantly higher than most steels, right? So where does that tell you we're going to see a lot of application? What's that? Yeah, right. Anything that we're concerned about efficiency, right? So aerospace, automotive. What are the other major industries that see a lot of titanium use? Biomedical, because it's biocompatible. All right. There's another big one. Right. It's a property that is not so easy up here. Right. So if I told you titanium has a very good passivating oxide layer, right? What would that imply to you guys? Good corrosion resistance, right? So places where you have hot corrosion issues, right? Chemical, petroleum, right, are also going to be key places. So this, we show our phase stability, well, not so much phase stability, but potential alloying space for titanium, right? The important things, though, carbon, nitrogen, oxygen, these guys go interstitial, right? Then you've got sort of a miscibility gap in terms of sizes, right? And then when you get to nickel, cobalt, iron, they will start to go substitutional, and you got a whole range of substitutional, potential substitutional solid alloying elements, right, up until molybdenum, zirconium, antimony. Then once you're above there, you're not going to, they're just too big to go in substitution. Okay, so first look at our phase diagram. We can classify these sort of the types of alloys that we're going to see as alpha alloys, right, which are HCP over the range of interest. Near alpha, where you're sort of at the upper end, right? Most of our commercial alloys, like Ti-6-4, are alpha and beta, what are classified as alpha and beta alloys, and so that means we're going to have we're going to be looking at using the alloys and processing the alloys in such a way that we have a mix of both phases, right? And then as we add more beta stabilizers, we get classified either as near beta or fully beta alloys. And then sort of a key thing to remember that is going to come across is that diffusion in the HCP is much slower than in the cubic phase.
Professor, is that mostly because of the phase structure itself, or the temperature?
The structure itself, right? So, okay. So let's talk about alpha for a little bit. So this is the first time we've looked at a hexagonal metal. So in FCC, slip systems are fairly straightforward, right? We've got 12 equivalents, right? They all are fairly easy, low energy. BCC was a little bit more complicated of a story because we had two basic families of slip systems. One was significantly easier than the other. HCP, things become a lot more complicated. We've got a lot of potential slip systems, right? So if we just look at the crystal structure, right? We expect, right, close packed plane along the close packed direction, right? So the most obvious intuitive slip system is going to be the basal slip system, right? But the prismatic also, the side here of our HCP unit cell, right? This also has a 1-1 bar 2-0 type direction on the 1-0 bar 1-0 plane, right? And it turns out that that's actually this prismatic system in titanium is easier than the basal system. We'll talk about why that is in a little bit, right? Whereas in magnesium, basal is much, much easier than prismatic. But if we look at these, we have a problem, right? So if I'm compressing on the C-axis of my crystal, what's my Schmidt factor for basal slip?
0.
0. What's my Schmidt factor for prismatic slip? Also 0, right? So compressing on the C-axis is never going to activate my two easy slip systems, right? So that means I need other less suited slip planes like pyramidal, right? So these are higher energy, right? More difficult to move. What's something else the system can do? Right? I can activate these different families of pyramidal slip, right? But then I can also twin, right? And depending on the temperature, the strain rate, and the alloy composition, twinning may be easier or harder, right? Pure titanium twins very readily, but in the commercially relevant alloys, not so much, right? Once we add a significant amount of beta stabilizers in there, we don't see a lot of twinning. So this slide here is general hexagonal, right? This isn't necessarily just limited to titanium. Okay, so it doesn't. No one can read this, right? Even the people in the front row probably can't read this. Okay. So basically, what I'm trying to point out here is that. Okay, so what's our critical what's the critical C over A ratio in HCP metals? .633, something like that. What do I mean by critical C over A ratio? Well, I mean, that will, right? But think back to Callister, right? To 2010, right? We worked out packing ratios in the different crystal systems. And there's probably a blurb about C over A ratio and how that affects packing, right? So the ideal C over A ratio is going to give you the most dense packing, right? Deviations from that are, all right. And so titanium, right, is about a 3% deviation from the ideal, right? And up here we see that the titanium has a C over A ratio of 1.58, right? 1.59, right? And so we have a smaller than ideal, right? And so if we look at the chart up here, we see that that zirconium, titanium, and beryllium tend to prefer prismatic slip over basal because of their deviation in C over A ratios, right? And so we can look at different dislocations that we see in the system, and sort of we can play with it geometrically, right? And basically see that we're going to prefer the prismatic system, right? It's going to give us the shortest dislocation, right? Shortest Berger's vector. So the pyral stress for prismatic is about a 1/4 of that for basal. I mean, not 1/4. Sorry. This is what I wanted to show. Where is my slide? I lost the slide. Okay. So here we see the difference between, so it's 14 versus 62 MPa, right, for prismatic versus basal slip. So a little more than a factor of 4. But if we add in interstitial oxygen, right, our interstitial oxygens are going to create a tetrahedral distortions in HCP just as they do in BCC, right? And that's going to give us a strong obstacle to dislocation motion. So going from 1% oxygen to 10% oxygen, we go from, on our easy prismatic, we go from 14 MPa to 90, and we go from 62 to 107 on the basal plane. So the interstitials actually reduce that and that the difference in energy to activate dislocations on the basal versus prismatic. So as we and because we also have a much higher temperature dependence, right? So here is basal and prismatic. Here's our pyramidal C plus A, right? And so we see a very large temperature dependence, right? Because we're not moving along our close packed planes, right? So the HCP in some ways behaves a lot like BCC in that we have a strong temperature dependence, but we also have a much stronger anisotropy that results, right? And this basically shows what I've just been saying is we alter our C to A ratio, right? We alter our interatomic spacing on both the basal and prismatic, right? So the right, as a low axial ratio, our spacing of our our C axis becomes less than, I'll get you just one second, becomes less than the A axis, so that becomes our C slip becomes easier, right? So titanium has an easier time than magnesium with slip along with accommodating deformation along the C axis, because it's easier to operate those C plus A systems, right? Whereas pure magnesium twins, much easier than titanium because it's easier to accommodate that deformation, right? Because of the ratio of spacing of the basal planes. Yeah, you had a question?
On the on the last slide, there's a graph with the different trend. Yeah, that one. So is the C plus A slip, is that pyramidal?
Yeah, C
Okay.
plus A pyramidal.
All right.
Yeah. Okay. So sort of was a little bit of a complicated discussion, right? Let me back it up. Just one second. So HCP, the easy slip mode is either going to be basal or prismatic, right? Because of the C over A ratio and the distance, and titanium and all the group 4 metals, so zirconium and hafnium, right, are going to tend to favor prismatic slip is going to be easier. Magnesium and beryllium, right, and things closer to the ideal C over A ratio are going to prefer basal slip, right, because of that same ratio, because of the same dependence of the C over A ratio. As we decrease the C over A ratio, we make our C into interplanar spacing along our C axis is less, so we are going to favor C slip, pyramidal slip over twinning a little bit more in titanium, right? So we do twin, but we twin less than magnesium, and we have easy prismatic slip, right? So that's the takeaway from all that sort of analysis, right? And we're going to have a very strong temperature dependence on ease of slip. Okay. So twinning occurs in commercial purity titanium, but as we increase solute concentration, we're going to get a lot less twinning, right? And the most common system is 1O bar 1-2 type twins, right? It has the smallest twinning shear, right? And it is going to tend, so here's the twin plane. If this becomes invariant, what does this do to our C-axis? What's that? Basically, you can think of the twinning as a rotation here. So our C-axis becomes aligned almost 90 degrees. It's like an 88-degree rotation, right? We can sort of visualize that here, right? Here's our twin plane. Here's the parent. Here's the twin, and we can see that we have roughly 90-degree reorientation of our C-axis. So what's that going to do to our properties? If a parent grain is well oriented for twinning, meaning it's now C-axis, say you're compressing on the C-axis, right, you're going to change to, right, you've got a 90-degree reorientation. So you go from easy twin direction to easy slip direction, right, or vice versa, right. So we have right, a huge degree of anisotropy because of that. So what does that imply about the effect of texture on the properties of a finished product if it's an alpha sheet, right? So if I have typically a rolled sheet is going to have a strong basal texture. So when it's finished, it's going to have a C-axis. Most of the basal poles are going to be orthogonal, right? So if I have, there's obviously going to be a strong difference between in-plane versus through thickness compression testing, right? So if I cut out a compression sample where my tensile axis is along the length of the seat, I'm mostly pushing on the A-axis, so I have easy prismatic slip. If I cut it out and I compress along the C-axis, right, obviously it's going to be much stronger. I'm going to have a higher yield because I'm compressing along the C-axis. So I'm activating modes which are much harder, right? But what about if I pull on, if I could somehow, if I cut out and do in-plane tension? So now I'm pulling on the C-axis. Am I going to have a similar response as compression, or will I have a yield asymmetry between tension and compression? I'm going to have a strong asymmetry, right? Because in one case, right, I'm going to be activating this slip system. In the other case, I'm going to be activating this twin system, right? Tension versus compressive twins, right? So when I activate the 1-0 bar 1-2, I'm effectively lengthening my, it's called a tensile twin because my C-axis in my new grain is longer, right? Okay, great. Work hardening, effective twinning on work hardening is basically the same as what we saw for steels, with one important difference, is that are our twin plane and our slip plane the same now? No. So twins and slip dislocations are going to interact much sooner in the process, right? So you don't see that region of low work hardening and then accelerated work hardening, right? You're going to see a region of accelerated work hardening right at the beginning. So twinning. So whenever you have a HCP system that twins, you're going to see a lot of work hardening right away. Texture develops very quickly in twins because now we are completely reorienting our crystal, right? We're not slowly rotating because of accumulating plastic shear, right? We're changing our C-axis through a military shear transformation, right? So texture development is very fast in twins. Okay, BCC slip or deformation, right? These are the same same that we talked about for steel. I just threw them in there for a refresher, right? With the 111, right, on the 110 plane being the primary slip mode. Yeah.
So what relative to steel can we expect the ductility to be of titanium?
For BCC is pretty comparable.
Oh, really?
Yeah, yeah. Right. So if you're in a beta alloy, you can get fairly significant. In many cases, you can potentially get a lot more ductility because you don't have the carbides that act as fracture initiation, right? But BCC materials in general can be very ductile.
What about the alpha?
Once you have significant alpha beta, you're going to have less ductility, right? Which causes a lot of problems. We have a lot of hot forming and hot working operations in whenever you have HCP present, because you need that you need the thermal energy to reduce your the amount of effort you need to get slip to occur, right? Okay. Titanium alloy. So we're going to classify our alloying elements as either alpha stabilizers, beta stabilizers, right? Our beta stabilizers, there's two classes, right? Beta isomorphous, right, which gives us an alpha plus beta field that comes all the way down, right, to room temperature operations, or beta eutectoid, where we come down, we have a eutectoid point, and then we go into alpha plus a secondary phase. Typically, this is going to be an aluminide, right, Ti3Al or TiAl, right? So we're going to talk a lot about the equivalent aluminum content, right? And then zirconium and tin are neutral. Why do you think these are neutral? Where is zirconium on the periodic table? It's immediately below it, right? It's a group 4 metal. It's also hexagonal, right? Tin is also HCP, right, with the C over A ratio. That's pretty dang close. So those have no real effect on the phase behavior. Okay, so we can break that out basically in the same way on their effect on the phase diagram. These are the isomorphs, right? The most important ones, vanadium, right? And then the eutectoid transformations. We're not going to worry about the alpha stabilizers and trying to categorize them into paratectic versus paratectoid, right? We get too much in there. Just the interstitials tend to give you something that's closer to a true paratectic than the solute. So if we look at the aluminum or titanium aluminum phase diagram, you can see it gets pretty nasty pretty quickly, right? There's a lot going on here, right? We're mostly going to be worrying just sort of in this region, right? But the picture is becomes, for all of these, becomes pretty complicated. Okay. So into into our specifics. So we've got alpha is HCP, beta is BCC, alpha and alpha prime. These are martensitic structures. And then we have omega phase, which is a non-close packed hexagonal, right? Which is something you probably haven't come across, right? So it's hexagonal, but it's not HCP. Right? It's a simple hexagonal structure, right? Right. Our alloying elements, of course, are interstitials, are alpha stabilizers. Aluminum being the most important. Beta stabilizers, vanadium, molybdenum, niobium, right? All of our BCC, right, tend to form our isomorphs, right? Eutectoids, chromium, iron, manganese, copper, silver, gold. Why you would add those is a little beyond me, but right. So those are the general classes. So if you just sort of, the important ones to know the effect are going to be aluminum and the interstitials, vanadium, molybdenum, titanium, and chromium, iron, manganese. Right. So if you know those, the effects of those elements, you're going to be good. Right. And just as before, we're going to classify these as either alpha alloys, near alpha alloys, age hardenable, titanium, copper. These basically think GP zones, right? So the behavior of these, we're going to see a lot of the same sorts of things kind of coming up. The alpha plus beta alloys, these are the important alloys, right? If everyone could name one titanium alloy, what is it? 6,4, right? Here, right? That's sort of like the archetype for the alpha plus beta alloys, right? And then the beta alloys. So perfect exam questions, right, is for me to ask, what's an issue with the properties, right, of a particular alloy? What are the advantages and disadvantages of certain alloy systems versus other alloy systems, right? And the general trends, right? So here we're pure alpha to pure beta, right? Adding beta stabilizers are going to tend to increase our heat treatment response to strengthening, right? Higher intermediate temperature strains because we're strengthening because we've got multiple phases. Fabricability because BCC is more ductile than HCP, right? Starting at pure beta and coming down, pure beta alloys, we add alpha, the stabilizers, creep strength, right? Because of the diffusion creep, right? Our diffusivity in HCP is so much less, and our weldability, right, is going to increase. So those are just some general trends. Tie 6,4 is here, right? So at the alpha plus beta, but closer to more like alpha alloys than some others. Okay, so if we think about pure alpha alloys, right, we're fully HCP, right? If we're fully HCP, we have, what mechanisms do we have available to strengthen? We're single phase, right? So we have solid solution strengthening, right? The most important being the interstitial oxygen, giving us strength. We've got a moderate Hall Petch effect, right? Significantly larger than aluminum, significantly smaller than steel, right? We can readily strengthen by cold work because we don't have a lot of ways for dislocations to get around each other, right? There, we can go up to beta quench quickly and get our alpha prime, alpha double prime martensitic phases, but we're not going to worry about this because this isn't a practical strengthening mechanism because we're mostly going to be interested in these for high temperature corrosion applications, right? Which means that we're in service, we're going to temper out all of our martensite, right? We're going to just transform it back to pure pure HCP, right? So pure alpha alloys are going to be used in places we need high temperature corrosion resistance. Yeah.
The martensite. What is the crystal structure of the martensite for titanium?
There's a couple. We'll get to those. Probably Wednesday. Right. You've got yeah. There's a couple different ways martensite can form. So. Okay. So basically, most of what we're going to be talking about with titanium is trying to exploit the beta to beta plus alpha transformation, right? To get our properties of interest, right? We also want to consider a couple different transformations: beta to our martensite, beta to omega, which is remember it's hexagonal, but it's not a close packed structure, and then beta to beta 1 and beta 2. These are beta 1 and beta 2 are both BCC structures, but they have different compositions and lattice parameters, right? Again, strong analogy to GP zones here, right? Where you basically have local concentration fluctuations, right? And we're going to try and optimize our processing to get the phases, combinations of the phases that are of most use for our properties. Most of the time, we're considering mechanical properties. Right? So the first is beta processing, right? So we take our alloy up above the transist, right? So we give it where's my pointer? Right. So up here we give it a beta solutionize treatment, right? We cool down, right? So this is going to give us allotropomorphic alpha along the prior beta boundaries, and it's also going to give us Widmanstätten like plates that grow into, right? Then we're going to take it back up high into the two-phase region, right? And then that's basically going to be high enough that our Widmanstätten structure is going to partially dissolve, right? And we're going to get these alpha plates that form internally in the grain, right? And these alpha ribs are going to coarsen, right? As we cool down, these are going to fully coarsen, and then we're going to nucleate small, fine secondary alpha particles within the beta region, and then we do another hold at a lower temperature called a stabilization temperature to fully develop the secondary alpha plates. So in this micrograph, what do we see? Right? The light regions are what structure? Alpha. And the dark is our beta, right? We can clearly see the prior beta grain boundary, right? This is the allotropomorphic alpha that formed on the grain boundary during our initial cooling from our beta solutionizing temperature. Right. Okay. And from this beta processing, depending on our cooling rates, right? If we think about if we cool quickly from here, from our solutionizing versus cooling slowly, we're going to have a very different morphology. If we cool slowly, we get what's called a colony microstructure, where we have big regions. Basically, you can think of these as like a colony of Widmanstätten plates, just like in steel, right? These are all one crystallographic variant, so everything in here is going to share a similar crystallographic orientation, separated by regions of beta, right?
Would packet be an accurate description of it? Like packets?
So they're, yeah, but the term, we don't use the terminology, right? You typically just say a colony, right? But conceptually the same, except in a packet you've got 6 different potential variants. Here we're thinking of a single variant, right? You've got fewer variants in this transformation than in the Martin-Siddick transformation for steels, right? So if you slow cool, you get these nice parallel plates. It looks pretty good, right? We nucleate grain boundary alpha here, right? And then the growth of these laths comes from the grain boundary. If we speed up our cooling, right, we get multiple crystallographic variants of our alpha laths that all form together, right? We have a much higher nucleation rate, right? And we get a tangle of different variants that tend to form these nice triangles, right? They form the triangles much in the same reason that Widmanstätten plates or will tend to form, or bainiter sheaths or twins will form the lenticular structure, right? We can minimize energies by nucleating groups of variants that come together. So I mentioned the words secondary alpha, right? So here's our primary alpha, right, that forms on our initial quench from our solutionizing, right? When we go to the alpha plus beta hold, these are going to thicken and will begin to nucleate these finer secondary alpha. You can see these lines in between the primary alpha laths, right? These are much more refined in scale, right? Very important for strengthening because now you can see how, right, we have basically very limited mean free path for dislocation motion in the beta phrase. So the existence of secondary alpha is really important for the strength of this, and the actual nucleation mechanism and how the secondary alpha nucleates is still really an open question. But most people seem to think it nucleates from the primary alpha. It comes out, but you get different variants, right? It's not like you only see the and we get different morphologies of secondary alpha. If we look, so this is right. This is this is a much coarser secondary alpha versus down here. Yeah.
How would you tell the difference in whether that is secondary or primary?
Yeah, it's just really the classification is when it forms, right? Whether it's forming on your initial quench from your solutionizing heat treatment, or whether it's forming on your alpha plus beta hold. But right, that's basically that hits at the point of this question to ponder thing is how everything forms. So, okay, so we're going to stop there.